Welcome to The Explainer. Today, we are cutting through all that complex jargon and those over-the-top sci-fi movie tropes to look at something that literally affects us every single day. We're going to demystify machine learning. Honestly, if you've ever wondered how your phone magically recognizes your face or how your favorite streaming service knows exactly what show you're going to want to binge next, well, you're already experiencing machine learning in action. But instead of getting bogged down in some crazy complex math right out of the gate, we're going to look at how these systems actually work by comparing them to something we all know really well: everyday human experience.
Okay, so here's a seemingly simple question for you. How exactly does a computer learn to tell the difference between a cat and a dog? I mean, a toddler can easily point and tell you if they're looking at a kitty or a puppy. But how do you actually program a computer to do that? Think about it. If you were to sit down and write the code manually, you'd have to write nearly impossible rules for every single possible shape of an ear, every slight variation in fur color, every weird contorted angle the animal might be sitting at, and every lighting condition imaginable. It's an endless, incredibly frustrating task. So let's look at how we solve that in Section 1, Beyond Traditional Programming. This comparison really perfectly captures the massive shift in how we tell computers what to do. With traditional programming, it's a lot like strictly following a rigid recipe. You, the programmer, give the computer exact step-by-step instructions. You know, if A happens, do B. Simple. But machine learning, that's a whole different ballgame. Instead of giving the computer the recipe, imagine you just feed it 1,000 different baked cakes. By tasting all of them, the computer figures out how to reverse engineer the recipe itself based on the patterns it finds. It's learning directly from the data, from the experience, rather than just blindly following manually written rules.
Which brings us right into Section 2, how machines actually learn.
Building one of these machine learning models from scratch is kind of like going on a journey, and it generally follows a 5-step process. Step 1, you collect data. We're talking images, text, audio recordings, sensor data, whatever you need. This is basically gathering your raw materials. Step 2, you prepare the data. Because let's face it, raw data is super messy. You gotta clean it up, handle any missing pieces, and format it so the computer can actually digest it. Then step 3, this is where the magic happens, train the model. You feed that beautifully prepared data into an algorithm, and the computer starts sniffing out those underlying patterns. But hold on, you aren't done yet. In step 4, you have to test the model using brand new data it has never seen before. Why? Because you need to know if it actually learned the concepts or if it just lazily memorized the answers. Finally, step 5, once it passes the test, it goes out into the real world to actually make predictions.
Let's break down how it learns in Section 3, the 3 learning styles.
First up is supervised learning. This is when we train a model using labeled data that already contains all the correct answers. Think of it exactly like studying with flashcards. You look at a card, you guess the answer, and then you flip it over to see if you were right. Because the data has the correct answers attached, the computer easily learns to connect the dots. This particular style is absolutely perfect for tasks like figuring out if an email is spam or not spam, or looking at historical real estate data to predict what a house is going to cost next year. Next, we've got unsupervised learning. Now here, models use entirely unlabeled data. There's no answer key. The model just has to discover patterns and relationships totally on its own. Imagine I drop a massive, chaotic mountain of mixed laundry right in front of you, but I don't give you any instructions on how to sort it. You probably just naturally start grouping things yourself, right? Maybe you separate by colors or put shirts in one pile and pants in another. That is exactly what unsupervised learning does. A really common real-world application of this is when companies use it for customer segmentation, grouping buyers based on how they shop without actually knowing what the distinct groups are beforehand. And the third style is reinforcement learning. This one is all about pure trial and error. The system gets rewards for good actions and penalties for bad ones. It is incredibly similar to teaching a dog a new trick. When the dog sits, boom, it gets a treat. When it jumps on the couch, timeout. Over time, the dog, or in this case the computer, figures out the absolute best strategy to maximize its rewards. Believe it or not, this specific type of learning is the primary driving force behind self-driving cars, advanced robotics, and even those AIs that can beat world champions at video games.
Moving on to the tech under the hood, Section 4, algorithms and deep learning. I want you to think of all these popular algorithms like a giant garage full of different types of engines. A developer is going to pick a completely different algorithm depending on the specific problem they're trying to solve. Need to predict a numerical value like a stock price? You might pull out the linear regression engine. Need to sort data based on what its nearest neighbors look like? Well, k-nearest neighbors is your go-to tool. Or maybe you want to combine a bunch of different decision pathways to get a super accurate result. You'd fire up a random forest. These algorithms are the foundational tools that let machines sniff out those hidden patterns in our data.
But sometimes the problem is just so vast and the data is so overwhelmingly massive that a standard engine just isn't going to cut it. And that brings us to deep learning. Deep learning is this highly specialized, superpowered branch of machine learning that utilizes artificial neural networks. And what's really wild is that these networks are actually inspired by the biological structure of the human brain. They feature all these layered nodes to process massive, complex amounts of information. And the rule of thumb here, the more data you feed a deep learning model, the smarter and more capable it becomes.
And the results of deep learning? They are truly staggering. We're talking about the tech behind ChatGPT, the facial recognition that securely unlocks your phone, the speech recognition inside your smart speakers, those crazy image generation tools everyone is playing with, and fully autonomous vehicles. These aren't some far-off concepts from a sci-fi novel. These are cutting-edge technologies actively running on deep learning frameworks right now, today. They're handling volumes of information that would literally be impossible for our human brains to process manually. Let's look at how this changes things in Section 5, Real-World Impact. Because this technology, it's universally applicable. In healthcare, machine learning is literally saving lives by predicting diseases and helping discover brand new drugs. In finance, it's silently operating in the background of your life, detecting credit card fraud in milliseconds before you even realize anything is wrong. In e-commerce, it's analyzing your behavior to give you those eerily accurate product recommendations. And in education, it is totally paving the way for personalized learning plans and 24/7 AI tutors. By automating all these repetitive tasks and just making better, faster decisions, it's transforming every major sector on the globe.
But it's definitely not all sunshine and rainbows. Let's cover Section 6, challenges, and what's next. See, the golden rule of machine learning is this: garbage in, garbage out. Bad data equals bad predictions. If your training data is poor quality, your model fails. But even more critically, if there are historical flaws, biases, or skewed perspectives in that training data, the model will faithfully and blindly learn and reproduce those exact same flaws, leading to some really unfair results. Add to that the massive privacy concerns of feeding our personal data into these models, the completely staggering hardware costs required to run them, and this tricky issue of interpretability. Sometimes even the brilliant creators don't fully understand exactly how their model arrived at a specific conclusion. It's a black box. Much like our own human experiences, the lessons a machine learns are only ever as good as the environment it learns them in. Still, despite the hurdles, this technology is evolving so rapidly. As our computing power increases and the sheer amount of data in the world continues to grow, the future promises vastly more intuitive AI assistants. We're looking at healthcare diagnostics that can spot issues long before a human doctor ever could, mind-blowing advanced robotics, incredibly safe autonomous vehicles, and educational systems entirely tailored to how you individually learn best. For sure, machine learning is going to remain one of the absolutely most important technologies shaping our future. And that brings us to the ultimate paradox of this whole thing. We are teaching these computers to learn from our human experiences, from our data. But our data, well, it's often deeply flawed and imperfect, right? So as these machines learn from us, are they just going to end up repeating our past mistakes? Or can we design them thoughtfully enough to actually help us build a better future? I'm going to leave you to think about that one. Thank you so much for exploring this topic with us today, and we'll see you in the next explainer.